Shrinking geometry of today's devices result in many challenges for testability. One key challenge is the ability to probe the signal at the desired test point. Probing in many cases happens on a via that is located away from the termination point. This causes reflections on the signal at the probe's location. Since the reflections are not present at the physical test point, the need is to remove them in order to simulate probing at the test point. Using SDLA Visualizer for Tektronix real-time oscilloscopes, it is easy to simulate probing at any point along the signal path. While link analysis applications have been primarily targeted at high-speed serial, DDR is another key application. In this example, a DDR signal has been acquired using a high-impedance probe solder to a via. As you can see, the waveform on the scope display contains reflections that are not caused by an impedance mismatch between the transmission line and the input impedance of the receiver. This is the result of the physical probing location, which is located away from the desired test point. In order to remove the reflections from the signal path, I must know the channel characteristics and receiver characteristics. The first step is to estimate the transmission line length between the physical probe location and the test point. This can easily be done on an oscilloscope using basic cursor measurements. The round-trip transmission line delay can be determined by placing the cursor on the incident rising edge and on the reflected rising edge. The transmission line delay can be determined by dividing this number by 2. In this example, the round-trip delay is 660 picoseconds, and thus the probe point is 330 picoseconds from the input of the receiver. The next step is to estimate the input impedance of the receiver. Again, this can be done by measuring the voltage level of the incident versus the reflected signal using cursors. Based on the voltage levels of the signal of 1.25 volts and 0.75 volts, the input impedance can be estimated at 200 ohms. The package model for the memory component was provided by the silicon vendor. Now that the transmission line delay, estimated input impedance, and package model are known, SDLA can be used to virtually probe the signal at the input to the receiver. SDLA is broken up into two circuits, the measurement and the simulation circuit. The measurement circuit is issued to describe the physical test connection to the device under test. This includes cables, probes, and fixtures. In order to fully describe the interaction of the test setup with the DUT, the measurement circuit must also describe the transmitter and receiver profiles, which includes package models and impedance models. The first step is to define the measurement circuit. This is done by selecting the de-embedded block in the SDLA. By selecting the high Z selection under probe, a high impedance probe appears in the transmission line. The next step is to describe the channel that is between the physical probe point and the receiver. This could be done using measured or simulated S parameters, but in this case we will use the measurement that we obtained earlier. By clicking on block B4, which is located to the right of the probe, I can select T-line and dial in the 30 picosecond delay. I can also label the block T-line to keep track of the element in the cascade. The S parameter model of the package can go in block B5. In the block, select the File tab, and under the model, select 4-port signal ended. Note that SDLA also supports 2-port S parameter, differential S parameters, FIR filters, transfer functions as data inputs. After selecting the S parameter model, the content of the file can be viewed by selecting the plot button. The default plot is the S parameter plot that shows the transmission, reflection, and cross-coupling terms. This can be used to validate the integrity of the S parameter model or to view the actual parameters. The model can also be viewed using a Smith chart plot, impedance versus frequency plot, or in the time domain. Based on the S parameter plot, I can easily identify that my through terms are specified on ports 1 through 3 and 2 through 4. I can quickly change the port assignments in SDLA to match this configuration. In addition, I could have used the check button to verify the ports are configured correctly. This block can be named PKG. The last step is to specify the input impedance of the receiver. By selecting the load block, the input impedance can be specified. Since we do not have S-parameter models of the DUT, we can enter a nominal impedance value, which we estimated to be 200 ohms. Now that the desired test points can be selected using the move function to move TP7 to the left of the load block. This will mark the virtual probing location, which can be turned on by clicking TP7 radio button. I can now assign TP7 to Math2. I'm now ready to apply the model. I simply press an SDLA and the transfer function is computed at TP7. I can see the resulting waveform on the scope display. While the waveform is not perfect, it is sufficient for doing parametric measurements. The accuracy of the de-embedded was limited by the use of approximate parameters for the transmission line and input impedance. Had S parameters been available that accurately represented the system, the results would have also been more accurate. In summary, this demo has shown how to use SDLA Visualizer to virtually probe a signal acquired through a high impedance probe.